Welcome to week 5. This week we have a set of 3 videos where we're going to be talking about image registration in sort of the broadest terms, but then more specifically about the idea of normalization, which is a specific example that's going to be important for doing group studies with fMRI. So what I want to do in this first video is talk about the aims for the week and then focus really on some of the issues associated with image registration. We really began talking about that last week when we talked about motion correction, because it's the same, that is a subset of the image registration things that we're going to be doing, but I just would like to make it a little bit more formal and try to explain the process and how the components relate to one another. So I want to try to introduce the idea of spaces and mapping between spaces, which is a fairly simple idea from linear algebra if you've had that. But if you haven't seen it before, it seems a little bit more complicated than probably it is. And I'm going to introduce the ideas of linear and nonlinear normalization, as well as talk about some of the advantages and disadvantages that they each have. And then finally, in the last short video this week, I want to talk about spatial smoothing, what it is, why we do it, and how to implement it. So, to just get into the fundamental issues associated with image registration this week, we're going to start by sort of noting that any 2 fMRI images or MRI images that we collect are, in some sense, they need to be, you need to find a correspondence between them if you want to do anything to link the 2 up. So for instance, normally we acquire a structural scan for all of our participants. We acquire functional data so that we can see what their brains are doing on a particular task. And one of the things we would typically like to do is show the activations that we see in the functional data on their structural scan. So you can see exactly which parts of their anatomy are responding in this particular paradigm. And that's easily said and less easily done, right? That requires finding the correspondence between the EPI, the echoplanar imaging, the fMRI scan, and the structural MRI scan. And there are multiple reasons for this, but one of the big ones is that typically they're just not acquired at the same time. You do all of your fMRI scanning and then you tell somebody to relax and you're going to collect a structural and they can fall asleep during that period of time. It's fine. But that often means that due to all of that little residual head movement things that we talked about previously, the heads aren't exactly in the same spot. Even though it's the same head, same person, same brain, it not necessarily in exactly the same location when you acquire the 2 scans, which means that the images aren't in good register. So for instance, if I were to just put like a little graph on these images, you can see that the EPI image is on the left, the structural image is on the right. And what I've done is I've highlighted, not a voxel, but a huge voxel in this case, just because it was easier to see it this way, in red. Right? And you can see that it's the same part of this graph. So if you consider the reference point to be the bottom right-hand corner, if you move up 5 grids and then you move in 7 grids, you're at that same red voxel. But the tissue that's there in that voxel is different. In the structural scan, it's very clearly the end of the lateral ventricle, right? I mean, that's the majority of the tissue that's there with some surrounding white matter. In contrast, because the EPI image is on a slightly different orientation, the head's angled kind of this way, you're actually primarily in gray matter and there's almost no ventricle component there whatsoever. So these images aren't aligned. They aren't in register. And you want them to be in register so that you can say, okay, well, data from this point in the grid corresponds to data from this point in the grid. I can overlay them and, for instance, show the activations on the structural scan. So what you want is the image to look like this, right? So now that square hasn't changed, but the EPI image itself is now in register with the structural scan. Right? And that is an image registration problem. That is to say, the reference in this case is the structural scan, the image that I'm going to affect is the functional scan, and I just want to make sure that it's in the same registration, same orientation, etc. as the structural scan. That's the question that we're trying to solve. Now, you probably recognize that that motion correction or realignment is a particular case of it. In this case, we picked a reference image that was also an EPI image. It was like the first one in the time series after you've gotten rid of the dummy volumes, if you're using SPM, for instance. So they're all EPI images, but the EPI images are in slightly different register because of head movement over time. In this case, that I'm showing here, we have a slightly harder problem because we need to link up images that don't have the same image properties. So let me just sort of unpack that a little bit in a minute. Before that, I just want to talk about some of the terms that we're going to use. So as per last week, we talked about image estimating. So the first step in this whole process is always trying to estimate what needs to be done to register one image to the other image. Then there's a resampling phase when we apply that transformation and create a new image. Every time we do that, we reduce a little bit of the image quality of the image that we're changing. So that is to say, we collected the data that we collected. We're then going to apply this, transformation to make a new image, but that isn't the image that we collected. So we've made a bunch of assumptions to do that related to interpolation, etc. And as a result, the image quality degrades a little bit. Similarly, it gets a little bit smoother, just a consequence of doing any interpolation. And this process is known as image registration. Sometimes it's known as co-registration, so that is linking two images together. But co-registration implies that you only have two, whereas image registration could be any number of images. And sometimes it's known as normalization. And normalization happens in a very specific case where the reference isn't a single image from a person. The normalization happens when you're trying to register one person's brain to sort of a group template brain so that you can start combining across individuals. And we'll talk about that in a minute. Okay, so the whole point here is that we're going to map from one space to another. The space is defined by the image that we acquired. We always are going to put a Cartesian coordinate system on it and treat it in terms of X, Y, and Z. And because each of the little components of the image is literally a tiny little cube or cuboid, and I say cuboid in case you don't make it isotropic voxel. So an isotropic voxel is one whose dimensions are the same in X, Y, and Z, 3 by 3 by 3. A non-isotropic voxel would be like a 3 by 3 by 2 voxel or something like that. Nonetheless, it's effectively, these are tiny little blocks, right? So we can always talk about what's in each of those individual voxels, but those voxels form a space. We have a reference point, a 0 point, and then we can talk about X, Y, and Z. And if you recall from last week, I said that X is always going to be left to right, Y is always going to be front to back, and Z is always going to be top to bottom. That's a convention that we're going to use in all of the neuroimaging that we do. And it is a convention, but it's an uncontroversial one. So please don't think about changing that one. So the image itself that you acquired defines a space. And we have a structural space in this case where we have a T1 weighted structural image on the left. We have a functional space on the right where we have an EPI image, an fMRI image, right? And you can see a couple things about it. Again, this is the same person's head. You can see that, one, the head isn't aligned the same. So in the structural scan, the head's up a little bit, whereas it's tilted a bit forward in the functional scan. But the other thing to show is that the field of view is a little bit different. You can see more of the brain, including like the cerebellum and the brainstem in the structural, than you can in the functional. So these are all things that we need to adjust. We didn't acquire the functional data related to the bottom part of the cerebellum and that brainstem, so we therefore need to make sure that we adjust the field of view so that we're looking at like with like. And as per last week, the way we're going to do this is we're going to define a cost function to say, well, how different are these two images? If they're very different, then there's a higher cost. If they're very similar, then there's a low cost. And what we're going to try to do is find a way to minimize that cost. And that minimization is our estimate of how to make the one registered with the other. So the simplest example is the one I gave you last week in terms of sum squared error. Here's an illustration of that. Basically, you can take one image, subtract the other image, and square the difference at each of the voxels, and even generate an error image if you're so interested. But all we're going to do, in fact, is calculate where, like the sum of all of those particular error scores at each of the voxels, and that gives us our overall error score. So you can see, for instance, that all of the area outside of the head that's black in those two images, when you subtract those two things together, you get this dull gray, because that means that there's no error there. The error occurs where the brain is. And this is what I mentioned just a few minutes ago, that it becomes harder to do cost functions across modalities. So that is to say, to compare a structural to a functional scan, because they can be the same tissue type and still give you very different signal. And that's the whole point of a T1 weighted image versus a T2 star weighted image, for instance. And look, here's a good example in this image. Under the crosshairs, even though these images are more or less aligned, and they're both showing something in the cerebral spinal fluid, in the lateral ventricles, it's got a very low value. It's a dark voxel in a T1 image, whereas in a T2 star image, it's a bright voxel. So if you said, well, are these the same? The answer is yes, conceptually they're the same. But if you said, are these intensities the same? The answer is no, they're very different. So just doing a sum squared error when you're trying to relate images from different modalities, like a structural and a functional or something along those lines, doesn't work anymore. So it's perfectly fine when you're doing motion correction, realignment, right? Because those are all images in the same modality. They're all functional scans by definition. And therefore, any given voxel's intensity doesn't change over time. I mean, if it's gray matter, it gives you a particular value. If it's white matter, it gives you a different value. But it doesn't change from image to image. That's not true if you're trying to link images from different modalities, which is something that we definitely want to do in order to, say, overlay activation onto a person's anatomy. So when we think about cost functions, and this is covered in more detail in the Poldrack book, there's a variety of functions that we can use. And this is not an exhaustive list, but it gives you a sort of a feel for what's out there. Least squares functions are what we talked about last week and are perfectly fine whenever you're doing stuff within the same modality. So for instance, when you're doing realignment. You can also use something called a normalized correlation score cost function. And this is also good for same modality, but it's important, like it is less sensitive to differences in brightness and contrast. So for instance, say you had somebody who was in the scanner and then had to get out because they needed to use the bathroom or something, and then came back and did another second run. And for whatever reason, the gradient coils have cooled slightly while they were out of the room, whatever, the intensity, the contrast is slightly different. Same person, same head. Nonetheless, the contrast is a little bit different. So therefore, a normalized correlation gives you a more robust measure than, for instance, a least squared would, even though it's still the same modality. In contrast, when you're comparing images from different modalities, like EPI to T1 to, say, a template or whatever. I mean, then there's multiple different ways of getting MR scans. There's proton density, there's T2, there's a lot of them. Then what you probably want to be using is something called a correlation ratio. Correlation ratio is giving you information about the way the components of the image relate to one another, and therefore that is conserved across these different modalities and allows you to register the two images. Probably the most robust method is something called mutual information, and this allows you to do even more different things, like linking an MRI scan to, say, a CT scan, a CAT scan. Where there's really, really different properties associated. And the advantage to using something like mutual information as a cost function is that it's very robust to a lot of violations of assumptions, right? But it's computationally more expensive. Whereas something like least squares, small violations of the assumptions can really screw you up, but it's super efficient to compute. So basically we're going from lots of assumptions but easy to very few assumptions but difficult. And the reality is that modern computers have the capability of doing things like mutual information pretty robustly these days. I mean, the speed and capability that they offer means that we don't normally need to worry about these kind of concerns anymore. But you should be aware of these options, and there's still different defaults depending on what you're doing. So for instance, normalized correlation is the default when doing realignment. Because there's no point in doing the extra work associated with mutual information. It really doesn't buy you anything. However, if you want to, you could. And last week, when we talked about realignment, we talked about it in the context of rigid body transformations, which is a 6 degrees of freedom transformation. It allows you to transform in X, Y, and Z in terms of translations, so that is movements in X, Y, and Z, and it does X, Y, and Z in terms of rotations as well, 6 degrees of freedom. It also allows you to adjust the field of view. So for instance, if you wanted to use a rigid body transformation to link a person's structural to their functional, basically you need to get the orientation right, but you also need to cut down the field of view, and that's fine. A rigid body transformation will do that, and it's very, very useful for realignment purposes. Right? So what I'm doing is I'm applying a transformation, a rigid body transformation of that structural, and just overlaying it on that functional. And you can see it's done a pretty good job. There are more sophisticated, but still linear transformations. And the most important one for our point is what's known as an affine transformation. So this is still purely linear, and it, rather than having 6 degrees of freedom, it now has 12 degrees of freedom. So you have the first 6 that I mentioned, the rigid body, but then you also have shearings, which allow you to stretch in X, Y, and Z, and then you have scalings. So that is to say you can stretch not just in a dimension, but across and maintain the size ratio. And that gives you 12 degrees of freedom, okay? The nice thing about a linear or an affine transformation is that there's only one solution. If you have 2 images and you apply a linear transformation, as long as you start with the same 2 images, you will always find exactly the same transformation. Doesn't matter what software you use, there is one solution and it's a solvable problem. And that makes it a very, very efficient thing to do because it's easy to calculate, and moreover, it doesn't vary from person to person, software to software, package to package, which is important because it means that everybody's solution is the same, right? Which makes them very comparable to one another. You can compare like with like when you're comparing linear transformations. The limit of a linear transformation is it doesn't really allow you to change the shape of anything, right? So for instance, there's no way to take this little sort of neutral face and turn it into a happy face, because in order to do that, I need to make a local transformation of shape. You can see that if I just put a grid on this and then put a grid on the second one, the only way I could make it work is if I change the smile specifically and leave the rest of it unchanged. Well, that's not a linear transformation because you're not doing the same thing to each of the voxels. So that's what's known as a nonlinear transformation. The disadvantage to nonlinear transformations is that there's essentially an infinite way to calculate them, and if you have two images and 2 different nonlinear transformation packages, you're going to completely come up with different solutions, which means that you're not necessarily comparing like with like. On the other hand, a nonlinear transformation is far more powerful in terms of making the 2 images more similar to one another. There's no linear transformation that's going to make this sort of grim face into the happy face, whereas it's a very trivial thing to do for a nonlinear transformation. Why does this matter? I mean, in theory, the shape shouldn't be a big deal, right? The shape of the brain didn't change whether you did a T1 scan or a T2 scan. It's still the same brain. However, as I pointed out again last week, there are shape effects that are created in terms of acquiring the data, and they relate to the distortions in the magnetic field, right? And that means that the EPI, the functional scan, and the structural scan, although they're very similar to one another, also have distortions that mean the shapes aren't the same. So for instance, here I'm overlaying the functional data from one participant on their own scan, and you can see it matches up incredibly well along the edges, and the ventricles are in the right place in terms of brighter signal on the ventricles, etc. But what's very obvious is that there's this distortion along the frontal poles due to the magnetic susceptibility artifact due to the sinus that runs along your midline. And that tissue signal has been pushed back in the EPI, but not in the structural image, which means that overall the shapes are very similar, but they're not identical. There is literally a shape difference in the data that was acquired from the same person at the same scanning session, depending on the modality of the acquisition. So nonlinear registration does offer these advantages, but it also comes with certain costs in the sense that it can possibly overfit your data. So this is an example of a patient who obviously has a midline lesion that you can see very here. So for instance, the area that's shown in red there on the top is an identification of the lesion, but hopefully you can see it fairly clearly in the images. And in this case, you don't want to use nonlinear registration to, for instance, fit it to a normal template, because this person doesn't have a normal brain. You don't want to fill in the hole, like correct the shape problem, because the shape problem is probably what you're interested in, the fact that it is a patient with this kind of a lesion. So you do need to be careful when you're using linear versus nonlinear image registration. In this particular example, what I've done is I've taken 20 subjects, 20 MRI scans from normal healthy people, so no patients, no holes in their brain, and I've registered them to a common template so that I could get rid of the fact that there are a lot of big differences between them and put them into a common space. And this is the kind of thing that you're going to do for any group study with fMR. And in fact, we'll talk about it in much more detail in the next video. But in one case, I did it using a purely affine set of transformations. And in one case, I used a nonlinear set of transformations. And you can see that the one on the right, the nonlinear, looks just a lot better. It's done a better job of linking up the anatomy of those subjects. There's still some variability. It's a little bit blurry, but it's not as blurry as the linear transformation, the affine transformation on the left. And at some level, that's very appealing. It seems like that's a really good thing to do because you want to match things up as best possible. But it's also important to bear in mind that these differences that you're trying to get rid of are real differences in people's heads, right? So you're taking the functional data that comes from slightly different shaped heads that are in different positions with different anatomical regions, and you're combining them. So this represents the reality of what's there in your data, and you're trying to get rid of that source of variability to make it look better. And I get that. That makes sense. But is that a sensible thing to do? And what I should say and be very clear about here is that I wrote a paper with Russ Poldrack years ago arguing that this is not a sensible thing to do. And my opinion is very much a minority opinion. The vast majority of the field think that a nonlinear registration for normal healthy brains is definitely the right way to go. I disagree with that, and I'm just sort of acknowledging that you're getting a non-standard perspective here. So if you look at there's a paper that Russ and I wrote called In Praise of Tedious Anatomy, and we try to make the arguments really clear there. But the summary of what I'm trying to say is that there's real variability here, and trying to get rid of that variability is an inaccurate representation of one of the things that's interesting across brains. So it's better to look at this sort of affine and blurrier brain because that shows you something about the underlying variability in the anatomy, which is important. It's not something that's due to head motion or anything else that's unrelated to what we're interested in, right? The anatomy is what we're interested in when we're looking at functional anatomy. So getting rid of it, trying to get rid of some of the inconvenience of the fact that people's heads are different, seems like the wrong way to go, in my opinion. Bear in mind, definitely a minority opinion.